Good morning, guys. So today is the third lecture in the course PYL102, and till now we have seen the properties of dielectric materials and different mechanism of polarization. In the last lecture, I ended by telling you that there are 5 types of polarization mechanism, in which at the end we saw there was something called ferroelectric ones, where we have some spontaneous polarization. So in today's lecture, we are going to see in detail those ferroelectric, piezoelectric, and pyroelectric materials. They're actually really important class of materials. That is being used in different industry and other electronic devices, because even the volatile memory devices as well. So uh, I'll mention which are used for for which purpose. For example, the piezoelectric materials, uh, which transform the electrical signal into a mechanical signal and used in force generators or things like this. And ferroelectric materials, they are used in capacitors and non-volatile memories. Okay, so they have really important practical aspect importance as well. So let's see in a bit detail what are ferroelectric materials. Okay, so I'll begin with ferroelectric materials. And we'll also see what is the difference between, let's say, the ferroelectric material that we are saying and the dielectric material that we just studied. So the ferroelectric materials, they are the one that possess a macroscopic spontaneous polarization. Okay, and this spontaneous polarization, you can reorient it using the external electric field. So we have something called spontaneous polarization. This is present in the system, and I'll tell you the reason why it is present in the material. And once you apply electric field, one can reorient it. Reorient the polarization, P or PS, or you want to call the polarization. And also the polarization in the ferroelectric material, it can exist even in the absence of electric field under certain range of temperature and pressure. Okay, however, in the dielectric material, if you remember, so once you apply electric field, then the polarization appear, right? Cause and effect. So you apply electric field, you have the effect as polarization. So that's the biggest difference also between a ferroelectric and dielectric material. And also in a dielectric material, the polarization can be generated uh, as I said, only by applying electric field. And once you remove the electric field, the polarization disappears. But in the ferroelectric material, it doesn't happen. So let me just pinpoint the thing that I just said. So polarization in the ferroelectric, let me just call them FM, okay? Because I'll be using them pretty frequently. And also, just to make a clear distinction, later when we will discuss magnetic material, there'll be something called ferromagnetic material. Oh, all right. So see, dielectric and magnetic, they go hand in hand, meaning I'll make a clear comparison. So there we, here in dielectric we have electric field, in the magnetic material we have magnetic field. So if you have a ferroelectric material in the in the after the application of the electric field. In magnetic materials, we'll have something called ferromagnetic material. Okay, so we'll see that later, but there also maybe I'll call that one also FM, or maybe I can call it FEM then, such that it will be clear that we are talking about electric one. Okay, so this is FEM. Just remove it. So the polarization in the ferroelectric material can exist in the absence of electric field, which I'll denote it in the absence of E, under certain range of temperature and pressure. And as I said, this is the major difference between ferroelectric and dielectric, because in dielectric, however, as we saw before, in dielectric, the polarization gets generated after the application of electric field. Application of electric field E, and once the electric field is removed, the polarization disappears. This we already saw in the last lecture as well. All right, so this was the dielectric thing, where polarization is only because of the electric field. However, in the ferroelectric one, it's spontaneous, it's there, and you just change the orientation of the polarization using the electric field. Now one can ask the question, why something is special in the ferroelectric material? So what's the reason? So the reason is, so the ferroelectric material, they have a crystal structure that doesn't have an inversion symmetry. Okay, so I'll also recall what do I mean by inversion symmetry. So crystal structure without inversion symmetry. I'll show you how this works with an example, but before that, let me tell you let me just recall you, because I believe that you all know what is inversion symmetry. So inversion symmetry is basically a transformation where R change to, if R goes from R plus R to minus R, the system remains invariant. Okay, so that's what I mean by inversion symmetry. So now let me show how if the crystal structure doesn't have inversion symmetry, the ferroelectricity appears, meaning there is a spontaneous polarization in the system. So the example that we will consider, it's BaTiO3. So this is a ferroelectric material, so it's barium titanate. All right, So let me draw its structure, its crystal structure. So I'll need a cubic geometry. Okay, sorry if my lines are not perfect. So the crystal structure is something like this. Okay, all right. So one more like that. So this is the cube. So I'm saying we have Ba2 plus, Di4 plus, and O2 minus. Okay. So let me draw with different colors. So first I'll draw the barium using blue. So barium is blue. They're sitting at the corners of the cubic crystal. So all the corners. So this is our barium. Then let me draw the oxygen atoms, which sits in the phase center. So the phase center would be here. So the oxygen is with green. Here, this phase, the bottom one, the left one. Now the problem appears in the front and back. Okay, so let's say this is our front, all right, the center, and I'll draw with dotted line the back one, but this is also the oxygen atom. Okay, so I can just draw a line such that it looks like a 3D structure. Okay, I can try. Okay, all right, so now comes the titanium atom. So in general, all right, in the equilibrium state, the titanium 4 sits at the center of the crystal structure. All right, so this is the schematic representation of the barium titanate. Now, let me come back. So now how the polarization appears. In the equilibrium state, you can see, because ions, all these ones, they are vibrating around their equilibrium position. So what happens if, let's say the temperature is pretty high, so this titanium, which is sitting at the center, it vibrates, for example, around X or Y or Z. The overall effect is, I mean, if you see, let's say the average configuration, it's going to stay at the center of the crystal structure. So if it happens at high temperature, when the titanium is, let's say, almost at the average position, is this the center of the cube, then we have something called paraelectric phase. All right, so this phase, it has inversion symmetry. So if, for example, I put my point of inversion at exactly on top of this red dot, so if I go plus X minus X, or plus Y minus Y plus Z minus Z, I'm going to see the same crystal structure. So this phase is inversion symmetric. Okay, and it's non-polar. This doesn't have any polarization, and that's why it's called paraelectric phase. But example, we are lowering our temperature. Now this titanium atom, it can be any of these 6 configurations, right? But because, let's say this, let me draw it using the different color. So this titanium atom, it can be somewhere over, okay, I can just, yeah, So something like this. So now this titanium atom, it can be shifted towards, let's say, if it is around positive x, or it can be, so then if it's somewhere over here, so you have an effective polarization along the, okay, let me just say this is our x, this is our z, and this is our y. Okay, so then we have a polarization along x-axis. Similarly, if this guy, the titanium atom, it's in the negative x, it's one of the configuration. So then the polarization is along minus x direction, or y, or minus y, or z, or minus v. So we have 6 configurations. Now what happens once you lower the temperature, then the crystal structure, instead of having a inversion symmetric system, it goes to one of these configuration where titanium atom is along one direction. Okay, so this gives you a spontaneous polarization in the system. So to begin with, if you see just one atom, there was no polarization, but the crystal structure, it arranges itself in a way that the polarization appears, and this is what we call spontaneous polarization, which is different from a dielectric material. And this happens, so as I said, lower the temperature, which implies you go to a ferroelectric phase, where the inversion symmetry is broken, because now if let's say this titanium is along plus x, now I don't have a center of inversion. Plus x is different from minus x, right? This ion is at some distance, for example 2 centimeter. The other left side green would be around 4 centimeter, so it's not inversion symmetric. So the inversion symmetry is broken. And also the important thing is the point where the transformation occurs. So I'll just write it down, it's really important, this point, the point, not the polar. The point where the transformation from high temperature to low temperature, there we have 2 phases now, right? At high temperature, as I defined, we have para-electric. At low, we have ferroelectric. So the point where the transformation from para-electric to ferroelectric phase appears is called Curie temperature. And we denote it using T and C. C for the Curie. So above Curie temperature, we have ferroelectric. Above Curie temperature, sorry, we have paraelectric, and below Curie temperature, we have ferroelectric. All right, and the crystal structure also above, because in the paraelectric phase we have perfect cube kind of crystal, and below we have tetragonal, because the titanium atom is not exact at the center, it's in one of the axes. Okay, so this was more or less what is a ferroelectric and how the spontaneous polarization occurs. It's because of the crystal structure. All right, so next we'll see the ferroelectric. Okay, before going, I would like to make another point that, see, it's not just the titanium atom which is moving. There are the barium and oxygen atoms are also moving, but the overall effect, it's such that you can think of just the titanium atom is moving around its equilibrium position. Otherwise, if I'll give you exact numbers, the atoms are moving of the order of picometer range. For example, barium atom moves of the range of 6 picometer, oxygen moves in the range of 3 picometer, and titanium moves in the range of 11 picometer. So that's why the overall effect is titanium has moved from its equilibrium position to along one of the direction. All right. Okay, so that was just a remark. Now we'll go to the ferroelectric domains. The region of a ferroelectric material in which a polarization is along a given direction, okay, that is known as a ferroelectric domain or vice domain. So I'll just write it down. The region of a ferroelectric material in which the polarization will be P is in a given direction is known as ferroelectric domain. I'll just show you via a picture so it will become clear. Ferroelectric domain or a vice domain. Okay, so let me just draw how the domains look like. So let's say this is our sample or system, and then this is a schematic representation. Okay, so I'm not showing you a SEM image or the actual image that comes out from an experiment. It's just a theoretical way to say it. So for example, let's say we are going to have different domains, and in each of these domains the polarization will be in some direction. If there is no applied electric field, till now, for example, I cannot say which direction the spontaneous magnetization is. Alright, so this is randomly arranged ferroelectric domains in ferroelectric. So domains are, they are this small region inside the ferroelectric material where P is along one direction. So let's say I'll just draw using, so this is one domain, okay, the this area, again this area is one domain. So each domain is separated from the other one, which is something called domain wall. So let me just write. Okay, before that, the size of a domain is of the order of, just to give you some numbers, from 100 nanometers to some millimeters, let's say a few millimeters, 1 millimeter. Okay, so this is the size of the domain. Now the thing, that line that I'm drawing that separates two domains, it is called the domain wall. So domain wall is the line, or let's say the thin, yeah, it's pretty thin. So the domain wall is of the order of angstroms in your system. So I can say domain walls or domain boundaries. Let me just write, separates different domains. And these are called the domain boundaries as well. So let me just write it down. Okay, so as I said, they are of the order of angstroms. Now one can ask the question, why, if you give me a system or any material, why all the the polarization, it's not oriented along a single direction. That's a genuine question, right? Why it's going into a patches, or there are different domains which are appearing. So the reason is, so if I give you a system, so if let's say we have a long range order, so meaning indefinitely the polarization is along one direction, then the free energy of the system increases from the standpoint of electric and mechanical energy. So that's why the system aligns the dipoles in such a way that it randomly orients the different polarization direction, which gives rise to the domains. All right. So it's because of the free energy that we cannot have a large, all the polarization pointing in one direction. So that's one thing. And then the next thing would be what happens if, let's say, we apply an electric field in the system. So if I also need another figure, more symmetric figure I'll show. Again, it's a schematic figure, not an actual SAM image, but approximately. So for example, let's say we have a domain. I'm showing you a diagram where we have different domains. So for example, I have something like this, okay, and I can say that my domains are this and this. So let me, all right, and I can say I have two different regions. So one is, let's say, this green region, which is this one, and this one. Similarly, this one, and okay, let me draw one more line here, and this one. Okay, so in the green region, the polarization is, let's say, along this direction, and in the white region, the polarization is along this direction. So this is the configuration in low electric field, low E. Now what happens if we apply a bit higher electric field? So this was our sample. And now the domains, so for example, if let's say we are applying an large electric field, high electric field along this direction, so the polarization along this direction will increase. So the domains, the area of the domain would increase, which is along the let's say plus Z direction, okay? So now instead of the figure A, we'll have figure B, and how it will look like, it will look like something like this. So this is, let's say, our green patch, which was this much big before. This is the green patch. This is again the green patch, and here's the last one. And this full region, it's the plus Z direction. These ones are along minus Z direction. Okay, so you see the effect of electric field is to increase the area of these domains along which you have applied the electric field. Okay, so let me just write this specifically. The application of electric field of E helps to align the domains, or you can say the polar region. Okay, and in the dielectric case, we saw that the polarization varies linearly with E, right? P was directly proportional to E. Actually, P is equal to chi E epsilon naught times E. This was the case in dielectric material, but it's not the case in the ferroelectric material. It's not exactly linear. So that's why I'm not writing the formula, the direct formula. It's a bit complicated. I'm not going into details of those formula. So I just want you to know the full mechanism, how the ferroelectricity appears, what are called the ferroelectric domains, what is domain wall. So if anywhere in your career, if you see any ferroelectric material or these kind of things, so you have an idea. Formulas, one can figure it out, but you should have an idea how the underlying physics is working. So the next thing that I want to cover in this ferroelectric one is the temperature dependence, and actually it is given a really nice name, which is called the Curie-Weiss law. So let me just write the dependence of dielectric constant on temperature. So what the Curie-Weiss law tells us, it tells us that the variation of dielectric constant in a parielectric phase, it can be given as something like this. So epsilon is equal to C divided by T minus TC, C, okay? Where TC is the Curie temperature. And the C is called the Curie-Weiss coefficient. Or you can also say just Curie constant. Okay, and this formula is mostly valid when T is greater than Tc, right? Because I'm telling you that this formula is valid for a paraelectric phase, right? Next, we'll discuss paraelectric hysteresis law. So this is going to be the last section in the ferroelectric one. However, I'm going to introduce piezo and pyroelectricity very briefly. Okay, so now the ferroelectric hysteresis loop. So basically, in this hysteresis loop, it's a relation, or it's a plot, it's a graph which shows the dependency of polarization or the displacement, dielectric displacement D, which I introduced in the previous lecture, on the electric field. Okay, so it's a, I should say it's it tells us how the dielectric constant epsilon r, or let's say P, or you can say the D, depends on the strength of the electric field. But before going into the detail of the hysteresis loop itself, I want to introduce few quantities which are really important to understand the hysteresis loop. So first one is called, so there are basically three quantities and phenomenon. So first one is saturation polarization, which will denote as PS. So as a its name suggests, so the polarization which has been saturated. So how do you achieve it? So as I said, as just we saw before, what does electric field do once we apply it in a ferroelectric material? The domains, the region, the area of the domain, it expands, right? So if we apply, let's say, pretty large electric field, so there will be a single domain in the system. And after that, if we'll apply the electric field, the polarization is not going to change because all the individual one, they have aligned in the same direction. So this is what is called the saturation polarization, meaning when we apply relatively high electric field, high E, so the material becomes single domain. And after this point, this polarization, which implies the polarization is said to be saturated. Either all the domains will align in the same direction, or there will be a large domain. So this is what is called PS. All right. The next definition which I want you to know is what is called poling. So poling, it's a process. So basically, in a ferroelectric material, if we have, let's say, substantially large amount of ferroelectric domains, which are aligned in with the applied electric field, okay, so that is what is called a poled ferroelectric, meaning we have large, substantial amount of aligned dipoles or polarization in one direction. That is what is called the pole dielectric, and the process of applying an electric field such that we have substantial fraction of domain is called poling. So I'll just write the poling is a process of applying an electric field in order to align a substantial fraction of domains. Okay, this is what is called poling. The next thing that I was to define is something called dipole. So as you can see, it has to be opposite of poling. So if, let's say, the material, it's exposed to high temperature, so we can dipole it, meaning dipoling means the domains undergo randomization, right? Opposite of poling, meaning aligning in random direction. So I'll just say the let's say dipoling, I'll call it. So dipoling would be where the domain align or domains undergo randomization. All right, so this is what is dipoling, and as an effect of dipoling, the net effect, it just disappears. The net ferroelectric effect in the system, it just goes away. So these are the three, let's say, basic PS is a quantity and remaining two are the processes. Now I'll introduce the hysteresis loop. So what is a hysteresis loop? It describes or it captures how the polarization or displacement, it varies as a function of electric field. Okay, so hysteresis loop describes how D or P varies as a function of E. Okay, so the applied electric field. Actually, in a ferroelectric material, okay, before going to that, just to remind you, what was D? D is equal to epsilon naught E plus P, right? So either we say that the relation between D and E or P and E. In the ferroelectric material, the P is generally significantly large compared to epsilon naught E. So that's why the difference between DE or PE loop, it doesn't change much. But in other systems, it can vary a bit. Okay, so now let me plot the hysteresis loop. So as I said, in the ferroelectric material, it doesn't matter whether I'm plotting D versus E or P versus E. So let me just say D versus E. Okay. Or I can say not I can say just P versus E because I'm gonna label few points. So now let's start with the origin. Okay, I want to go with the negative x's also. So let's start from the origin. So as we so at E is equal to 0, in the beginning, all the dipoles are or the domains are oriented in different direction in the ferroelectric. So we have a 0 polarization. So now, if we increase the electric field, there is a spontaneous polarization which appears, and it is linear for a small e, right? It behaves like the normal dielectric. So it is kind of linear in the beginning. For example, let's say till a point A. Okay, but beyond that, it becomes non-linear, but it has to increase. So it goes something like this. And after a point, for example, let's say B, it just becomes almost the slope is really small. So why? Because we have reached saturation polarization. So the electric field is pretty large, such that all the we have a large domain, or most of the polarization are along one direction. Okay, so let's say this point is B, this was A, and here it's something C, where we have achieved the saturation, PS, saturation polarization. So I can say, if I'll draw for example, this dotted line back, this is PS, okay, the saturation polarization. So this is when we go from, let's say, 0 to A to B to C, okay. And as I said, the slope between B and C is really small, which also tells us that the dielectric constant would be small, right? This epsilon would be pretty small in this region. All right. The next thing would be, now what happens? Imagine now when we decrease the electric field. So when we decrease the electric field, so instead of following the same path that we came back, what happens? There is a substantial polarization which remains in the system. So meaning that even if, let's say, if I come back from C to B to, if I go further, instead of going to O, I'll go somewhere which is, let's say, this point is D. All right, so the polarization, it doesn't go to 0, even though the applied electric field is 0. So why this happens? Actually, even though the electric field is zero, it's all the domain. They don't change their polarization direction. All right, even though the applied electric field is zero. So that's why there is this. This is called Raman polarization. I'll denote this thing as PR. And just to point out, this thing was PS. Sorry, PR. PR is the Raman polarization. Um, okay, so now what is the path? The path is OABC. Now we decrease the electric field. Instead of going to A, we reach the D. And this gives us the Raman polarization PR. Now, if you want to remove this Raman polarization, we have to apply an electric field in the opposite direction, right? That's how the PR would go away. So now, let's say we increase our electric field in opposite direction. So we go something like this. So we go from D to, let's say, F. So F is a point where the polarization becomes zero. And as you see, we need a finite electric field in opposite direction for that, and it is denoted as EC. Okay, the coercive field. So let me just write down EC is called the coercive field, or the electric field in a reverse direction. All right, so you can think of in a similar way that what happens if we go back beyond meaning if I keep on increasing the electric field in the opposite direction. So let me just denote it using the dotted line. So I'll reach again a saturation point, let's say it's G. All right, then the polarization saturates in the minus E direction, and again we can come back. All right, so instead of going to zero, our polarization is minus PR right now. It's in the opposite way. And if I want to remove this PR, this minus PR from the system, we'll have to increase the electric field now in the positive direction. So then this is also EC. So I can also say that this point is H. And similarly, if we'll go beyond, we'll continue like this. All right. So this is a typical DE hysteresis loop, or PE hysteresis loop. Okay, so I hope the thing is clear. It's just that once we reverse the direction, the polarization, it doesn't follow the same path that that the system took before. So we went from O to A to B, C, but when we decrease the electric field, instead of going to O, we went to D. The system keeps some polarization in it. Now we want to remove D, we have to apply an electric field in the opposite direction. So that's how we went from D to F. And this reverse electric field, it's called coercive field. The similar process will happen if we'll go in the negative E direction. That's how we went from F to G, and then G to H, following the hysteresis loop.